Welcome back to another fun and exciting day of geometry. Today we are in the third lesson of chapter 4. We're going to start the class period today with something that brings us back quite a bit to some ideas that we've done a long time ago but are still pertinent and will be as we move forward. So I'm going to ask to see if you can truly test your own ability to do these two warm-up problems to solve the thing on the left. Remember, there's an equal sign, so I can solve that. And then on the one on the right, I want you to multiply. So we will start. I'll pause the video, see if you can get after it, and then we will go. Now, looking at this first problem, remember when we're solving any quadratic equation, I know this is quadratic because of the square that's up there, I need to make sure that one side is equal to 0. So what I'm going to do is I'm going to start by adding 2 to both sides of this equation, which is going to yield for me x squared minus 8x plus 12 equals 0. And now at this point, you have options. Remember, you can use the quadratic formula, or we can use our friend factoring, and that's going to be my method of choice. I'm going to solve this quadratic by factoring in the zero product property. So remember, factoring is using our area model and our x, and we multiply the 12 and the x squared together to make 12x squared. Then that middle term of negative 8x goes on the bottom, and I need two numbers that multiply to 12 and add to negative 8. Off the top of my head, I know that those are going to be negative 6x and negative 2x. And those go right here in my box, negative 6x, negative 2x. And so then my factors are going to be x and x. Those multiply to make x squared. This is going to be negative 2, and this is going to be negative 6. So what I just did is I factored that quadratic up above to be x minus 6 and x minus 2. And that's still equal to 0. I just changed the form from standard form to factored form, but now I need to use the zero product property. And that's where I take each of the factors and I set them equal to 0, and I solve for x individually, and in doing so I get x equals 6 and x equals 2. And what these solutions represent are the values of x that make the original equation equal to negative 2. And I solved it by setting it equal to 0 and factoring. So a lot of people neglect this first step up here of setting it equal to 0. But then we also want to make sure that you can use the quadratic formula, but factoring also works as well. On problem number 2, don't you dare sin mathematically by distributing this 2 into both of those terms. Anytime we see some quantity squared with a plus or minus in between the two terms, we need to make sure that we rewrite that as two linear factors. What I mean by that is x plus 4 times x plus 4. A lot of us struggled then on the next step on our last test that we just took. When multiplying these two binomials together, we need to create an area model or a box. This is going backwards from the previous problem. Now I have the dimensions of the box of x plus 4 and x plus 4. And so this is where I go through and I fill out the product of each of the smaller boxes within my area model, which would be this. Then I combine all my like terms to make x squared plus 8x plus 16. I don't need to solve anything. All I'm doing is moving this into standard form or multiplying it together. So there's a trip down memory lane and some important algebraic skills that we still need to hold on to as we move forward. Alright, so what we're going to do today is what the textbook calls expanding the trig table. And what we've been doing over the last few days is we've found the slope ratios for several angles, but we are very limited to be able to use the slope angles that are currently in our trig table. And what they mean by that is this is the trig table toolkit. Essentially what we've talked about so far is an 11-degree angle, a 22-degree angle, and then a 45-degree angle. And then the other lesson the other day we learned about the complements of each of these. So I know an 11-degree angle has a slope ratio of 1/5. We said, well, hey, the complementary angle with 11 degrees is 79, and what we do is we just flip that to make that 5/1. So these two things go together, and we can do the same thing with 22 degrees. We know that that had a slope ratio of 2/5, and then the complement to 22 degrees would be 68 degrees, and so therefore that slope ratio would be 5/2. we know that our 45-degree slope ratio is 1 over 1. So what we're going to do is we're going to expand on that today as we move forward. So on problem number 23, it says, on your paper, draw a slope triangle with a slope of 45 degrees. So if I were to take a triangle, something like this, and this is 45 degrees, what they're saying is what would happen to this angle if I increased this angle to 55 degrees? What would happen to the slope ratio? Well, what happens is that this side length right here would have to become longer, or this side length is increasing as it goes up, and therefore this side length going down, the vertical component, I misspoke earlier, that hypotenuse is staying relatively the same, and the thing that's going to change are the vertical and the horizontal components. And so the vertical component becomes longer as your angle increases more and more and more. And we're going to apply that now into this lesson down here, looking at this 55-degree angle. So you can use this as a reference down here if you need to take a screenshot of this trig table toolkit. It lists all of these different angle measurements with their corresponding slope ratios. So I can see for a 55-degree angle, the slope ratio is 10 over 7. And so the way that we would solve for x now is we know that, hey, this 55-degree angle, I know that that has a slope ratio of 10 over 7, and we can use that in order to set up a proportion with the sides that I have in this triangle. And so the sides in this triangle, I have the change in y 8 over the change in x, which I don't know. So I can write that as 8 over x, and now I cross multiply to make 10x equals 56. And when I solve for x, I divide both sides by 10, and I get x equals 5.6. And so what we are just noticing right now at this point is that we can use all of these different angles and their complements to be able to solve for different side lengths within right triangles if we know a specific angle. So moving on to problem number 24 then, it says copy each of the following triangles on your paper, decide whether or not the measurements are possible. If the triangle is possible, find the value of x or theta, and what you're going to do is you're going to use this resource page down here. So if you need to, again, take a screenshot of this to have it, that's perfectly fine. But we're going to use these ratios and their corresponding angles to help us solve for these triangles up here as we move forward. So for example, as I look at this first problem, I see a 70-degree angle. I'm going to look down at my trig table toolkit, and I see 70 degrees that has a slope ratio of 2.747 or 13.737 over, so what was that, one more time, sorry, I just have to look, my memory's not great right now, 13.737 over 5, 13.737 over 5. So that ratio has to be the same as my change in y over the change in x, which would be x over 10. So in that instance, what I'm going to do is I'm going to cross multiply, and I'm going to get 5x equals 130.37. And then I'm going to divide both sides by 5, and when I do that, I'm going to get that x is approximately 27.47. So using that table down below, I would be able to solve for that missing side length. So I'm going to ask that you do the same thing. Work through a couple of these problems, see if you can use the table to help you find them, and then we will compare our work. All right, let's see how we did. This ratio, 50 over 6 in the triangles, or in our triangle toolkit, was correlated to a 83-degree angle. So on letter B, this would turn out to be 83 degrees, the measure of theta right here, as this 50 over 6 is in our table. 10 over 1 on letter C, that corresponds to a change in y over change in x is 10. That was an 84-degree angle according to our trig table toolkit. On letter D, we have an 8-degree slope angle relationship, which is found right here, 26 over 185. So I set up that ratio with the one that I have in my triangle, solve for x, got 142.3. This one is not possible. You can't have a side length of 0 on letter E. That's not going to work out too well. On letter F, an 89-degree slope angle. Well, that ratio right here is 5,200 or 729 over 100. And so I set that equal to x over 2, solve for x, and I got 114.58. And in this triangle right here, that's not possible as well. You can't have two 90-degree angles. That is not possible, as those triangles would exceed, or those angles on the interior would exceed 180 degrees. So hopefully you did okay there using the trig table toolkit to help us find missing angles or sides within certain triangles. So the last thing for today's lesson was merely looking at different relationships of angles and their corresponding sides, and as we increase the angle, we should see that the change in y over the change in x gets larger and larger, and that should make sense. If I have a triangle with a small angle right here, the change in y versus my change in x, that's not going to be very big since my y value is small in that case. However, if I increase the angle, my y value is much larger and x is much smaller. So as I increase this angle right here, so does my change in y over change in x. That also changes. One thing just to discuss at the end of our lesson today, we're going to briefly talk about something called a sequence, which you hit on in Algebra 1. And a sequence is merely just a list of numbers. So this list right here is a list of numbers going 4, 7, 10, 13. And this one right here, where you're adding the same amount over and over again of 3, this is called an arithmetic sequence. And an arithmetic sequence is very similar to a linear function. It's just a list of numbers that go up or down by the same amount over and over again. And so the equation that we use for it is almost exactly like what we would use for a linear function. It's y equals m, where m is merely the value that you're adding back and forth, and b is the starting point where you're starting within your function. So they go through that right here. Notice how you're going up by 3, and my first term is 4, and so that might be kind of confusing, like, hey, why isn't this value 4? Well, this is my first term, so what would my 0th term be if there were such a word? Well, that would be going backwards 3 units, which would put it at 1, kind of like the y-intercept. So that's what I have right here. 3n plus 1 would be the explicit formula that I have that would model that sequence. The other kind of sequence that we're just going to briefly talk about is something called a geometric sequence, which is very similar to exponential functions. And if you don't recall exponential functions, as a brief reminder, an exponential function is something that looks like y equals a times b to the x, where the a value is your starting amount and the b value is your multiplier. And so this is things that would be multiplying or repeated multiplication over and over again, as in this case, from 6 to 18 I multiply by 3. From 18 to 54 I multiply by 3. That's repeated multiplication. And so if you have a sequence of numbers that is repeatedly multiplying over and over again by the same quantity, we refer to that sequence of numbers as geometric. And so we would model a geometric sequence very similar to an exponential function. Noticing here a times b to the n, that looks very, very similar to a times b to the x. We just use this letter n to denote that it is a sequence and not a function. It's a little bit mathy, but I just wanted to get your mind introduced to these two different types of sequences, something that is arithmetic is modeled by linear growth, and something that is geometric is multiplied by exponential growth. And we're going to work a little bit more sequences as we move forward. As always, feel free to swing by office hours anytime. I'm available, eager to help you if need be. Hope you all stay safe, stay healthy, and we'll talk soon.